Hi everyone, nice to meet you. My name is Hyunjune Shin, the first author of Teacher as a Lenient Expert, Teacher-Agnostic Data-Free Knowledge Distillation. This is a joint work with Doan Choi. Let's get started. Today's presentation is as follows. First, we introduce the background of data-free knowledge distillation and analyze the catastrophic problem of existing methods that we discovered. After that, we will present our solution and the experimental results. This is background. Knowledge distillation is one of the powerful compression techniques that transfers knowledge from a large model called the teacher model to a smaller model called the student model. General solution is trained to minimize the distance between the outputs of the two models by using the real data learned by the teacher model. However, the assumption that we can always access the real data is unrealistic. Therefore, we need to consider situations in which we cannot access to real data. And data-free knowledge distillation is a research area to address this issue. DFKD utilizes the synthetic samples using generative network instead of real data as a means of knowledge transferring. Therefore, the main study focuses on how to define effective loss function for generative network. So let's see how the generative network is trained in DFKD. Most DFKD methods are composed of representation, crisp-prior, and adversarial loss. Firstly, the representation loss is consistently research area, aiming to mimic real data. Due to the unavailability of real data, this loss function is commonly employed in most DFKD methods. Secondly, the crisp-prior loss enforces the generator to produce samples that are precise enough to be well predicted by teacher. Lastly, the adversarial loss enforces the generator to produce hard samples for enhancing the diversity of synthetic samples. As you may have sensed, the crisp-prior and adversarial loss from a complementary relationship to ensure that synthetic samples with sufficient precision and diversity. So most DFKD methods are based on representation, focusing on crisp-prior or adversarial loss. Recently, there have been cases where both loss terms are used together. From now on, we will introduce the newly discovered issue. If we define the problem that we have discovered in a single sentence, it is existing DFKD methods are quite sensitive to different teacher models. In other words, when transferring knowledge from two different teacher models with similar performance, one student have excellent performance, but the other doesn't. The left figure shows the student accuracy over epochs when transferring knowledge from two different teacher models with similar performance. Three representative methods of DFKD were distinguished by color. As you can see, when knowledge was transferred from the dotted line teacher, the performance was notably lower compared to the solid line teacher. We analyzed the reasons for the failure of each method. Firstly, when focusing on crisp-prior, even though this original goal is generating precise samples, sometimes there is a catastrophic failure by excessively generating too easy samples of a specific category. Second, when focusing on adversarial loss, there is a problem of generating unexpected low-quality samples with the purpose of generating hard samples. Even when combining the crisp-prior and adversarial loss, generator cannot achieve to proper balance. Especially, we focus on catastrophic failure of first case, crisp-prior, so we conducted detailed experiment to precisely analyze the principles of crisp-prior. This is analysis of crisp-prior. First, let's see what is crisp-prior. Crisp-prior enforces the generator to produce samples that are precise enough to be well predicted by teacher model. In more detail, generator that takes noise as input synthesize samples. These synthesized samples are then fed forward to a pre-trained teacher model and then applying cross-entropy loss between output and one-hot label obtained by algorithmic function. However, contrary to the original goal of synthesizing precise samples, we highlight two issues with crisp-prior. The first is degradation of sample diversity, and second is the failure to properly achieve the original goal, leading to incomplete quality control. First, we talk about lower sample diversity. To investigate the impact of classifier on the diversity of synthesized samples, we vary the intensity of classifier and examine the generated samples. From a quantitative perspective, we measure the FID score to evaluate the realism and diversity of the samples, synthetic samples. From a qualitative perspective, we visualize images of airplane and dogs. FID is a metric that measures the difference in mean and variance between the distribution of real and synthetic samples. So the lower the better. As seen in the left figure, the FID score increases with a slope of approximately 2.8 as the intensity of classifier. In other words, a problem arises where classifier compromise diversity. As shown in the right figure, when classifier is set to 0, diverse images are generated. The next problem is the inability to properly achieve the original goal, named incomplete quality control. To investigate the impact of classifier about the quality control, we train generator with classifier but removing adversarial loss. The reason is adversarial loss is known to be a major component of low quality sample. The below figure represents the result for our detailed experiment. We visually show one of the samples. The synthesized sample is such low quality that it's difficult to classify. We denote such sample as X in a 2D visualization of feature vectors. In other words, the classifier cannot achieve its original goal even without any interference. Furthermore, we fed this low quality sample to the teacher model. We observed that teacher model also become confused. Next, we will introduce our proposed method. Our first proposal is eliminating classifier in the generator loss term. By minimizing only the representation loss and adversarial loss, we lead the generator to more freely meet the distribution of real data. However, it could potentially lead to higher risk of generating low-quality samples. To address this issue, we propose a sample selection method that filters only the samples validated by the teacher model. In other words, among the samples generated by the freely trained generator, we select and utilize only the samples validated by the teacher model. The detailed operation of sample selection is as follows. First, when the synthesized samples are input to the teacher model, we can calculate cross-enthalpy loss between output and categories for each sample. We call this loss as the per-sample loss. Upon further consideration, the per-sample loss means how confidently each sample verifies with the category defined by the teacher model. After that, we feed each per-sample loss into a Gaussian mixture model composed of 2 Gaussian distributions using EM algorithm. The Gaussian distribution with a smaller mean, called as G-small, represents the distribution with a low per-sample loss and is considered trustful by teacher model. Conversely, the distribution with a large mean, called G-big, represents a distribution with high per-sample loss and is considered untrustworthy by teacher model. We select sample when the probability of posterior distribution of G-small is bigger than a certain threshold, tau. In other words, it is a method of selecting samples when the probability of belonging the distribution validated by teacher model is bigger than a certain threshold, tau. We set the tau value to 0.5. That's all our core proposed method. Next is the effect of sample selection. In the figure, it can be observed that by removing the classifier, more low-quality samples marked with X are generated. However, after applying sample selection, it is confirmed that all low-quality samples have been removed. Here is the overall process of TDF-KD, our proposed method. The generator taking noise as input, synthesized X hat, and to maximize the running of feature level information from real data. Representation loss is applied to all X hat. This is indicated by the gray dotted line. At the same time, only samples validated by the teacher model is applied to distillation loss and adversarial loss, guiding stable knowledge transfer and preventing the generators adversarial learning from deviating significantly. This is indicated by the blue dotted line. Here is our experimental result. We compared the performance across 5 different teacher models with similar performance on CIPHER 10 and CIPHER 100 dataset. We have 2 main strengths. Firstly, teacher-agnostic robustness, which represents the maximum performance difference between a given teacher and student model. Secondly, teacher-agnostic stability. indicating how stably the student model learns. It was measured as the average performance over a specific epoch period in the later stage of training. It was consistently confirmed that the proposed TAD FKT shows superior performance in both aspects. In other words, the TAD FKT demonstrates a consistently high and stable performance independent to given teacher model. Finally, this is our conclusion. We discovered that existing difficulty methods are quite sensitive to different teacher models because generator is not always guaranteed to synthesize precise yet diverse sample. We conducted the first study on teacher-agnostic DFKD. And by replacing the crisp prior restriction with our sample schema, we can achieve enhanced quality control and leading us to propose the TAD-FKD method. In our experiment, TAD-FKD has demonstrated remarkable robustness and stability across various teacher models. So this is end of presentation, and the implementation code is uploaded in GitHub page. This is my email address, and if you guys have any question, feel free to contact me anytime. Thank you.